Okay. We have the toolbox to talk about 60% of this class right now. Let's start applying it. Okay, what we're always going to do is we're going to try to model a system. We're going to start at the Schrödinger equation, and we're going to apply either different assumptions, look at different potentials, and solve for those systems. So let's talk about the Schrödinger equation a little bit. So if we look at it historically, we had the Bohr model of the atom. They knew that that was flawed. People started tackling this, and one of the best ways that they found to model these systems was through something called the Schrödinger equation. Or what they wanted to do was get the energy of a system. So we seek to determine the energy a quantum mechanical particle. Utilizing ideas from classical physics, what is the energy made up of? It's always what two types of energy? Yep. So we'll have kinetic energy plus, what was the other one, Lily? Yeah. Okay. We're going to keep this in mind when we start looking at quantum systems. You looked at it on the daily problem, but if you want to get the kinetic energy out of a quantum system, what do you need to know? You got to know the kinetic energy operator, and you got to know the wave function for the system. If you want to know the potential energy, what do you got to know? Yeah, exactly. There's an operator hanging out there for any system we want to look at, which is awesome. We just got to figure it out or rationalize it. So what we're going to do is we're going to start with a wave function. We don't know what that wave function is. So let's try to make this simple. And consider a system traveling in one direction. What direction do you want to pick? We got 3. What's your preference, Will? Thank God. I was like, no one starts with Y, and if they do, you shouldn't trust them. And Z, that's just a lunatic. All right, so what does our wave function depend on? Yep, X and T. X is position. What's T? Time. So this is a time-dependent wave function. Just following the 6th postulate of quantum mechanics we had. Okay, what we're going to assume is, to make our lives even easier, let's assume psi does not change with time. So how is that going to change? Yep. So that's one of the first assumptions we make, is that some systems just don't depend on time. We won't worry about it. Okay. We already talked a little bit about total energy. You already told me this, but I just want to write it down. The total energy of a system is an observable. Since it's an observable, what must there be? There has to be an operator. So I'm looking for the total energy of our system. In quantum mechanics, how would I have to compute that? What two things do I need to know? Yep, you got to know the operator and the wave function. Okay, so we need psi. We got to operate on it, and then we get our scalar. What symbol are we going to give this operator? Yeah, that's the Hamiltonian operator. Okay. Oh, and our wave function only depends on what? Yeah, I should have probably put this in. Okay, we can break that Hamiltonian operator up into two other operators. What two other operators could we have? Yep, kinetic energy operator and potential energy operator. That's exactly right. Okay, now we got to devise a kinetic energy operator and a potential energy operator. To do this, let's jump back to classical mechanics. In your physics classes, you probably proved this once before. That's true. Do we know any operators we could plug in here and just apply an operator to get the kinetic energy? Or have we looked at any examples that utilize a certain operator in here? Yeah. Do you remember what that was equal to? Yep, negative I h bar. What derivative with respect to what in this case? Yep. Okay. Let's plug in to get K. K hat. So what we'll do is this. We can plug that in. So we get negative I h bar if we square this, what are we going to get out? Yep. Negative h bar. And what about that derivative? Yep. and then we just have 2m. So when you guys had to utilize this on the daily problem, that's where that came from. That kinetic energy operator comes from. Okay, so now we can change this expression a bit. So therefore, let's just plug in stuff here. We get negative h bar squared, 2m The nice part is this kinetic energy operator only changes a little bit as you add more dimensions, but it always looks this way. The potential is a different story. This is really where you find unique systems. So if you want to consider a particle in a box that has a certain potential, you want to consider a particle on a sphere that has a different potential, you want to consider a particle in a hydrogen atom that has a different potential. This is going to be the thing that changes when we look at different systems. Does that make sense? Stuff's always going to, or the particles are always going to be in motion. This is where like the individuality of the systems comes to play. And we'll talk about that next time. Okay? So for now, understand how does this thing come about? This is our generic Schrödinger equation. 1D and understand what do these components mean. If you can do that, the rest of the class is just mathematics. And then applying it and seeing weird and wacky stuff. Are there any questions about that?